Okay, so real quick and close and have a look up here, and I'll let you work here. I promise I'll give you a chance to work on those assignments that I'm putting up here in just a second that cover 4.1. But for today, I want to look at something interesting. Okay, so we got to just quickly review a couple concepts. So if we do something like, oh, let's say I give you something like this. Okay, what's the answer? So what is that asking us to do? What would we call that? Say it again. Could call it an integral. What else could we call it? Antiderivative. Okay. Trying to find the integral or the antiderivative of x squared plus 3. So this is just calculus jeopardy, right? And we've got a whole list. I'll give you a printout of this. In fact, I'll even do that today. I'll give you an updated printout that not only has the derivative standard forms that you know, but it also has each corresponding antiderivative. But all they are is just the reverse of the derivative standard forms, right? So we can anti-differentiate or integrate term by term. So what am I going to get from this first term? If we play calculus jeopardy, what's the antiderivative of x squared?
2x cubed.
X cubed over 3. Good. Right? Does that make sense? Because if I take the derivative, the 3 will cancel the 1/3, and then I end up with my x squared, right?
2b's.
Okay. What about this one? What's that going to be? 3x. There you go. Good. And then I have to have a constant at the end, right? So that's what I would call a general solution, right? Because I only know the answer to within a constant, right? That's a whole infinite family of curves. Each trajectory is going to have a different value of the constant, okay? But what happens, so let's label it. So this is general solution. What if I add another condition here, though? What if I say something like, let's say, I'll write it a different way. What if our solution has to go through the point 0.05? So what do we call that? This is the last thing we talked about on Tuesday. Could that be a particular condition, right? And we're looking for a particular solution, right? A specific trajectory, okay? So this one, it's a particular condition, but because the independent variable has a value of 0, what might we call this? Yeah, okay, good. So that's an initial condition. And if we apply that, what do we get? So we know that our function, or the solution up here we got was f of x equals x cubed over 3 plus 3x plus c. This is telling us right here essentially that f of 0 equals 5, right? And so what do we find? If I let x go to 0, I'm going to get 5 equals 0 plus 0 plus c, right? So the value of c, in order to honor this initial condition, c has to be 5, right? And so our particular solution then ends up being okay, so there's our particular solution. And I don't know if we got through it. Did we finish that last example?
Yeah.
We did, where we had two particular conditions? Remember, let's do, we did finish it? Okay. All right, so then, here's what we get to do today that's really cool. So what I want to do now is let's look at, here's our, this is going to be our differential equation. It's going to be a second order differential equation. It's going to be a second derivative. So we know that the G is a constant. Okay, so that's saying the second derivative of S with respect to T equals G. Okay, let's think about this in terms of kinematics. S is the position function, right? So if S is the position function, what's S prime?
Velocity.
Velocity, okay.
And then the second derivative is g, or acceleration.
Acceleration. Okay, so this is just another way of saying acceleration equals g. What do you suppose, physics types, what do you suppose that g is standing for?
Gravity.
Yeah, gravity. What do you know? Acceleration of gravity. And let's be a little more specific here. Let's say negative g, where g we're going to define as 9.8 meters per second squared. Okay? Make sense? Okay, so we can, we'll just write in terms of numbers. We don't need to write in terms of a symbol. We'll just say this. And we'll just leave the units off, standard units, meters per second squared. What's significant about 9.8? That is the acceleration of gravity at the surface of the Earth, right? Okay, so, and it is constant, isn't it? That's one thing we know, and that's a relatively easy thing to measure. Now, here's what's cool. By using calculus, we can take that one simple fact, and we can derive some equations that you might be familiar with. Okay, so let's solve this differential equation by anti-differentiating. Okay, so if I take the antiderivative of S double prime, what's that going to be?
9.8x.
Okay, so, right, so we could say that S prime of t, which is the same thing as V of t, is going to be the antiderivative of negative 9.8 dt, right? Does that make sense? Okay. I hate to do this, I'm going to make one more switcheroo here. We'll plug in this value later, but I want to, instead of just coming up with numbers for the acceleration of gravity on Earth, let's be more general. Let's just call this A, where A is constant, and then we can put in any value we want. What we'll do on Earth is we'll plug in the value negative 9.8, right? So that's the acceleration we get on Earth, negative because it's pointing down, right? But anytime we have a constant acceleration, we're going to get the same result just in terms of A. Okay, so that's going to give us here A dt, where A is a constant. So what's the solution to this differential equation then? You already told me. A t plus, call it C1. Okay. All right, so then we get a solution here for velocity as a function of time, but what about this C1? Any suggestions what we could do with that C1?
Maybe just see.
We could, yeah. But we'd like to be able to come up with something more useful. I mean, how did we deal with the constant before?
Could we make that initial speed?
Ah, okay. Yeah, what would we say if we let t equal 0 and we just solve for velocity? What is v of 0. That's, by definition, that's the velocity at time 0. That's our initial velocity, right? So we'll just call that v naught. In physics, remember that means our initial velocity, right? Yeah, and so if we evaluate this function at 0, then what do we get? Well, we get v of 0 equals a times 0 plus c. Well, that's just 0, right? And so we end up with v naught equals c1. Okay, and so that ought to look familiar then, right? We end up with the equation v of t equals at plus v naught. Now we flipped that around typically in kinematics, and we wrote it as v naught plus at. But that's kinematics equation number 2, right? For people that are in physics, right? Okay. Well, we could go one step further. V is s dot, or s prime. And really it's just s dot, isn't it? Because we're differentiating with respect to t. Okay. So if we anti-differentiate that one, if we're starting with the differential equation now, v of t, which is s prime of t, equals, I'll write it this way, v naught plus at. If I want to undo that derivative and solve for position, I'm just going to anti-differentiate, right? So we're going to get the antiderivative of, the integrand is going to be v naught plus at all times dt. What's that give us? This term's going to be, remember v naught's a constant, right? Because it's just the initial velocity. So what's the antiderivative of v naught dt? V naught t, good. Plus, what's the antiderivative of at dt?
1/2 t squared.
Okay, good. A times t squared over 2, right? Which we could just write as 1/2 a t squared plus, call it c2, right? Okay, well, what could we suggest maybe the meaning of c2 is then?
Initial position.
Yeah, if we just evaluate this at 0, we get, s of 0 equals 0 plus 0 plus c2. S of 0 is just s naught, right? And so we come up with then, the equation s of t equals, I'm going to put the c2 first. Let's just move it to the front. And it's going to be initial position plus initial velocity times time plus 1/2 at squared. That probably looks familiar, right? That's kinematics equation number 3. Okay, and so, we could write it that way, or the way we oftentimes write it is we'll say position minus initial position is what? Delta x, or delta s in this case, right? So we get displacement equals v naught t plus 1/2 at squared, right? There it is. Okay, how about that? So finally, we get to expand our view of physics a little bit when we start introducing calculus into it. Okay? All right. I'm going to put up those assignments and let you work on those. And then we'll look at something a little different tomorrow.